this video, we're going to talk about how we can apply Newton's second law for rotation, that is that the sum of torques is equal to the moment of inertia I times the angular acceleration alpha. So the rotational equivalent of F equals ma, this is now sum of torques equals I alpha. So Newton's second law for rotation to a single rotating object. So the first step in your problem solving, very methodical, very much like Newton's second law and linear motion. We're going to have very specific steps that you always follow when you're doing a Newton's second law problem, whether or not it's for linear motion or rotational motion. So here we go. So the first one is going to be to draw our version of a free body diagram. Now, before, we could treat the object as a point particle because we were only concerned about the acceleration of the center of mass. And so it just mattered what forces were acting, not where. Now, we need to draw what's called an extended free body diagram. Oops, I spelled that wrong. Extended free body diagram, which is going to show all the forces acting, but also where they act. And so in this case, you're going to show all the forces acting and where they act relative to some pivot, right? Because you're going to be rotating around it. So where they act relative to a pivot point. So we need the R and the F to find the torque R cross F. Basically, what we're going to do is draw a couple examples. So let's just say that I had a long bar and it was pivoted at one end. And let's say that I'm applying a force to it to kind of try to make the bar go down. And let's say that it's in a gravitational field. So I'm kind of holding it horizontal like this, and then it can rotate downwards. So if it's just like this to start and it's about to rotate down. So I'm going to apply a force to kind of help it go. So let's just add that force in here. Then I might have the force acting, but what also matters in this diagram now is the distance R that force acts. So I would also be very mindful of making sure that I knew what that R was so that I could find the torque. And then what do you do about the weight of an object if you're drawing an extended free body diagram? Where would the weight of the object act? And you might say, well, it acts sort of at every point, and it, sure, but that's a very useful thing about the center of mass. That weight acts as if all that mass was at the center of mass. So what you also have then is at the center of mass, you're going to have the weight force mg. So that's going to be an important point, is that if the object has a weight force acting on it, so if the object has its weight as a force acting on it, like not at the pivot, if it's at the pivot, we often don't care, then the weight acts at the center of mass. And so that's what I've described here, is that would be the weight acting at the center of mass. And if it's a uniform object, then the center of mass is at the center, right? So this then would be, whatever that distance, the length of the rod divided by 2. Okay, so that's an example of an extended free body diagram. Another example is, let's look at a pulley. So a pulley is going to be rotated around its center, right? But then you're going to have forces that act on it, say tangentially, because the string that's wrapped around it is going to be coming off. And no matter what direction the string comes off in, it's always acting tangentially to the pulley. So let's say I have a pulley, say with 2 forces on it like this. Now, here's the thing. We used to say, and this is very important, we used to say that the tension in a single part, in a single rope, a single continuous rope, was the same on both sides of a pulley, right? In linear world, that's what we did. And that's because we didn't care about the mass of the pulley. So we weren't worrying about the angular acceleration of the pulley. And so let me call this T1 and T2. If T1 equals T2, so I have to say here, note, if T1 equals T2, then there's going to be no net torque, so the pulley can't spin. That's now because we're considering the pulley as an object with mass. So therefore, we need to have unequal tensions on both sides. Even though it's a continuous string, our tensions now are not a single tension in the rope, but the tension on each side of the pulley. So in this case, let's say the pulley is rotating as shown that way. So let's say that's the direction that if we view the angular acceleration. Alpha, if we use our right-hand rule for omega, and let's say that was omega and that alpha was speeding up, let's say that alpha is out of the page. So say that alpha is out of the page, so that's going to be in the positive z direction, right? Then that means I need to have T1 be stronger than T2, right? Because that's going to be my, what I call my dominant torque. Then in that case, then T1 would have to be greater than T2 in order to make the pulley spin. Okay, so when you have this free body diagram with a pulley, you're going to have different tensions on each side, so you have to have subscripts. Now let's think about what the lever arm is, right? Because in order to get the torque, we need to worry about the angle between R and F. And so in this case here, the lever arm always points from the center of the pulley, from the pivot, to where the force is applied. So that would be my lever arm here. That would be for T2. That would be my what so-called lever arm, the distance from the pivot to where the force is applied, the R in R cross F. And it's always perpendicular to the tension because it's going to be tangential. The tension is always coming off tangentially, right? So that's going to be T2. And then if I change colors over here, then the R for tension 1 would again point from the pivot to where the force is applied. Each force has its own, R that you're going to use in R cross F. And again, this one is perpendicular to T1. So the good news there is that my angle is always 90. So note, for pulleys, theta equals 90 degrees between R and F. And remember all the way back when we first started talking about tension, a fundamental rule of tension is that it always points along the rope away from the object. So note the tensions point away from the pulleys. So those are the two most common types of things you might have. You can have other examples as well. So as a last example of a free body diagram, you might have a square that is being pivoted. And you could pivot something wherever you want, just put a hinge there. Let's say in this case that it's just a square and, maybe somebody's trying to, tip it over relative to some pivot point down here, and they're applying, a force up here. So then in that case, you might draw this diagram as your extended free body diagram, and then you would kind of clearly indicate your R so that you're ready and set up for doing R cross F. Now, excuse me, that's going to be what we do for our extended free body diagrams. So that's just step one. That's basically learning to draw our free body diagrams, but in an extended way. Okay, so now what we are going to do is move on to step two. And if we remember from linear world, we would draw our free body diagram, and then we would do the sum of forces, sum of individual forces from the diagram, and then we would set it equal to plus or minus MA or 0. We're going to do that similar idea. You're going to draw a diagram. We're going to do the sum of torques, the left-hand side, from the individual torques, and then we're going to set it equal to plus I alpha minus I alpha or 0. Okay, so step two is then going to be our so-called left-hand side, which is going to be that we are going to have the sum of torques. And in this case, there's two main ways to go about finding the direction of a torque. Sometimes you might want to just say that the torques that are in the direction of the angular acceleration are always positive, and torques opposite the angular acceleration are negative. Or you might try to use a convention where torques out of the page are positive and torques into the page are negative. It's entirely your choice, and you're just going to have to be careful on the sign that you assigned a plus I alpha or minus alpha. In this particular video, I'm going to go with the one where we stick to a fixed convention. Let's say that I'm going to define positive alpha to be in positive z hat direction, which would be out of the page. And so therefore, positive torque will also be that direction. So I want to do my sum of the individual torques. So I'm going to have the torque from some force 1, and then, plus the torque from some force 2, and I'm going to just add those up. And a key idea here is that I'm going to get each individual each individual torque from R cross F, just like we've already done with torques. So what I would do then is I would have basically R1, F1, sine theta 1, the angle between R1 and F1, and that might end up being plus or minus depending on if it's in the, into the page or out of the page with the right-hand rule, and then plus or minus R2, F2, sine theta 2, plus or minus however many I have. So that's going to be the sort of thing I write down in this step. Before it would be like just your forces or the components of your force along your axis. Here we're looking at each torque term, which way it points, into the page, out of the page, and then just adding up all of our torques. Torques that act at the pivot are 0, right? Because R is 0. So we don't have to worry about torques that act at our pivot point. So that's step 2, is the sum of these individual torques. And then now we're ready for step 3, which is going to be putting it all together. So set the sum of your individual torques equal to plus or minus I alpha. Oops, I don't want the vector sign over alpha in that case, because at this point alpha will be my magnitude of my angular acceleration, or 0 if it's not accelerating. So if you just have a static equilibrium case, which is something that we'll get to in a few modules. All right, so I'm going to set the sum of torque equal to I alpha, and I'm going to choose plus I alpha if alpha is in the positive z direction, and then minus I alpha if alpha is in the negative z direction, so into the page. And then choose 0 if alpha equals 0. So that's going to basically be what I do, and then I end up with the equation of motion for that object. So I would then have something that's going to look like plus or minus R1, F1 magnitudes sine theta 1 plus or minus R2, F2 sine theta 2. And remember, it's not always sine. I'm putting sine because theta 1 and theta 2 are specifically the angle between R and F, but that's not always the angle you're given in the problem. And then I'm going to say that that equals, and then plus or minus I alpha. And so I will make that note here so that you have that if you refer back to this, is you can use cosine in this equation. It depends on what angle you're given in the problem or whether you want to adjust your angle. And the other thing here that you'll notice is that we still have I in this. So that's going to lead us to step 4. Often you need to solve for I. So that's an additional step we didn't have in linear step. So often you need to solve or look up if it's on the chart for like a pulley or an object that you know, moment of inertia. Oops. Inertia, and plug that in for I. So that additional step where you're going to want to solve for that moment of inertia. Okay, so that then results in your equation of motion. It'll allow you to solve for your angular acceleration. And as one last note, if you're asked for the tangential acceleration of a point on the object, that's great, because if you found alpha, you can get the tangential acceleration. Remember that those are related. So just recall that we have this relationship, which is that alpha is equal to A sub t over R, so that we can then get the tangential acceleration from alpha. So you still go through the same process to find a tangential acceleration of a rotating object. You just be a single point on the rotating object, depending on the point it was talking about. All right, let me know if you have any questions.